Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to compute the moment of inertia using the integral formulation. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
In this example, we're being asked to compute the moment of inertia about the centroidal x prime axis, then use the parallel axis theorem to compute the moment of inertia about the base x-axis, which we see is down here. So the first thing we're going to do is we notice that this is a rectangle again. So this is kind of similar to the previous example. But again, we're being asked to compute the moment of inertia first about the centroidal x prime axis. So what I'm going to do is, I know this is a rectangle, so I'm going to go ahead and establish my centroidal x prime and y prime axes here, right in the middle. And we know for a rectangle where the centroid is, it's half of each dimension. So this will be h over 2, of course. And then the base dimension will be at b over 2. All right. So that's how we're gonna establish things to begin with. Now, when we are computing ix prime, okay, so to compute ix prime, we need to use the x prime, y prime axes. All right. So that's what can be a little tricky sometimes. We are first being asked to compute the moment of inertia about the centroidal x prime axis. And again, we're using that integral form. So the integral form is still going to have the same general form. It's still integral of a y squared dA, right? So dA. But the difference is we should probably go ahead and say it's y prime squared, okay? Since we're really basing it off of the centroidal axes right now, okay? So it's almost like at this point, it's almost like you can just ignore these regular x and y axes because we're really concerned with the centroidal axes at the moment. So that's why, just to be consistent, I'm saying y prime here because I'm referring to my centroidal axes, okay? So the next thing we want to do is, similar to the previous example, we are going to use horizontal slices, okay? And again, we're doing that because we said it's best to orient your dA slices to be parallel to the axis that you want the moment of inertia about. So I'm going to use these horizontal dA slices here, okay? And then, of course, I have a differential height dy prime, okay? And then I'm going to have a width, a total width, of course, of x, okay? X right there, which really is a total width of b, but it's going to end up going from negative b over 2 to positive b over 2, okay? So again, in relation to the x prime axis, we're really looking at negative b over 2 and positive b over 2. So right now, maybe almost like you're ignoring the black x and y axes, okay? So here we go. We're going to say dA is, of course, x dy, okay? Dy prime, sorry. And how do we piece this together? Well, again, x is going to be just the base dimension, the total base dimension b, right? It's this right here. This is the dimension x. And even though our origin is right here in the middle, the total base dimension has a width of b, okay? So we can substitute that into our integral. We're going to say ix prime equals the integral, and we're going to have y prime squared, and then we're going to have b dy prime. So very similar to the process we saw in the previous example. Now, what are my integration limits now? Well, again, I am integrating with respect to dy prime now, all right? And I'm referring to these centroidal axes. So should I be integrating from 0 to h? No. 0 to h would be based on these global xy axes here, but I'm looking at these centroidal axes that are going right through the middle of my rectangle. So based on this origin, the centroidal origin, I should be integrating from negative h over 2 to positive h over 2. Okay, again, forget about the xy axes. You're looking at the x prime, y prime axes. You're going from negative h over 2 to positive h over 2. All right, so we're going to put that in here, negative h over 2 to positive h over 2 here. Okay, and now we're ready to perform this integration. We're going to end up with b times y prime cubed over 3, okay? And then we're evaluating from negative h over 2 to positive h over 2. So we're going to have to do upper limit minus lower limit. So we're going to say I sub x prime equals, and I'm just going to factor out this b over 3 to kind of get it out of the way. And we're going to have h over 2 cubed, and then we're going to have a minus negative h over 2 cubed. Again, upper limit minus lower limit. So let's punch this through. We're going to say I sub x prime equals b over 3, and then we're going to get an h cubed over 8, and then we're going to say minus a negative h cubed over 8. All right, mind your algebra here. And so then ix prime is going to be b over 3 times the quantity, and those two negatives become a positive, so we get 2h cubed over 8, and then we can easily see that this reduces to let's see, this 2 cancels with this and becomes a 1/4, so we get bh cubed over 12 finally. And that's part of our answer. Now the next part was use the parallel axis theorem, to then compute I sub x about this x-axis, right? That's the second part of our problem. So now we're going to say apply parallel axis theorem to compute I sub x. And so what does that tell us? Remember, what does the parallel axis theorem say? It says as long as you know the moment of inertia about an axis through a centroid, then you can calculate the moment of inertia about any axis parallel to the axis you already know I about. So I'm going to say I sub x equals ix prime plus a times d sub y squared. Well, where's d sub y here? Well, again, remember from our notes, d sub y is the perpendicular distance from the x prime axis to the x-axis here. And in our case, it's just going to be h over 2, right? That's d sub y right here, all right? So again, we'll make a note of that. D sub y equals perpendicular distance between x and x prime axes. And so in our case for this example, it's just equal to h over 2. So now I can apply this parallel axis theorem, and I can say I sub x equals bh cubed over 12. That's what I just calculated. Plus the area is b times h over 2 squared. And doing a little bit of algebra here, I'm going to have bh cubed over 12 plus bh cubed over 4. Okay, when I combine all this, I get bh cubed over 4. And I'm going to get a least common denominator here. So I got bh cubed over 12 plus 3 bh cubed over 12, and then I'm going to end up with 4bh cubed over 12. So of course I finally get I sub x equals bh cubed over 3. And look at that. that is actually the same value that we calculated in the previous example. In the previous example, we directly calculated I sub x using the integral form. In this example, we computed Ix prime using the integral form about the centroidal axis, and then we applied the parallel axis theorem to get I sub x, and we come to the same conclusion. And we'll make a note here. We're to say where x is the horizontal axis at the rectangle base, which is, again, the same conclusion we came to in the previous example.